All right. There seems to be a lot of questions on number 8, which I expected. The problem was that people were asking me the questions 30 minutes before the assignment was due. So there's not a lot I can do for you when it's 30 minutes till and you're running into issues, right? So what I'm going to do is this. I want everyone to turn in what they have, and then I'm going to offer, you can go home after I talk about number 8, you can go home and redo it and turn it in next class, all right? But I want to know what you have now. Yes?
Are you recording?
Yes? Why?
No, I just wanted to go back and doing it.
Oh yeah, I'm recording. All right, so I will collect what you have, please. Pass those up. Were all the other ones okay? No? Which other ones cause problems? 7. What was 7? Oh, the right cylinder.
The volume.
Volume one? Okay. I think you turn out on that one, I believe it's something like the radius is, I don't know, something root 3. I don't know. I'll have to go back and look. 3 root 3 and 6 root 3?
Yeah.
Something like that.
3 root 6.
Yeah, something like that. Okay. I'm going to talk briefly about this because we really don't have a lot of time for this. If you would have asked me how to do this problem a day or two ahead of time, I would have reminded you that, well, you're trying to find, I would assume that you could at least get the objective function and the constraint. The objective function would have been the distance function, right, which would have been the square root of x squared plus y squared plus z squared. So I'm assuming you at least got that much of it. And then there are 2 constraints, right? Constraint 1 is this one, move everything to one side. The second constraint is this one, right? Okay, so the problem that people were having was that you're going to have lambda and mu, and it was really that derivative, it was the partial of f that sucked because it had the root in it, right? And that root screws everything up. It just makes it a lot harder than it has to be. So I'm going to show you something that you may have seen in Cal 1, but it's been a long time. So I'm just going to show it to you now, put it into your memory bank. Don't ever forget it because it'll be something that'll become useful if you ever have to find a maximum of a function involving a square root ever again. And that's this simple fact. If we call this right here d, right, for distance, right? That's what it was. We are trying to find the minimum and the maximum of d, right? That's what we're trying to figure out, the x, the y, and the z that will give you a minimum and maximum of that distance function constrained to those 2 curves. This is equivalent to finding the min and max of d squared. In other words, the highest and lowest points of this function are also the highest and lowest points of this function, which means that you can square it to start the problem. All right? And that makes your life easier because what you do is you say, okay, instead of looking at f, I'm going to look at f squared, which is that. And then your partials are so much easier to work with. And then you go back and you'll get an x, y, and a z. That x, y, and z give you the max and min of d squared. But I'm telling you that those values will also correspond to the max and min of d. So it really just comes down to something like this. If this function right here, f, by itself with the square root, if that is a positive function, which it is, right? It's above the x-axis, or it could touch. if you have a function that is always above the x-axis or possibly touching, I'll just do this. Okay? If that's your f function, which I call d, if I square it, it's going to be a new picture, isn't it? All the x-intercepts are still in the same place though, right? Because when you square 0, it's the same thing. All these values right here get squared are still going to correspond to highest and lowest values. All right? That's the key to that problem. Now, it can be done without that, but the problem is much easier this way. So I recommend, if you want, you don't have to, go back and do that problem, do d squared. Just remember though, oh, it doesn't ask you for the actual distance, does it? So just find the points. So the x, y, and z that you find will be your closest and furthest. But when you go back to actually compute the distance, if you really wanted to know how far, you would have to go back to this one, not to d squared. All right. How many of you had seen that before? D squared? Okay, that can save your ass in a lot of situations where you're trying to find the maximum of a function. Okay. I have another exam. They just keep coming. But this one's not due till April 6th. Take one, pass. All right, there's only three. Whoa, what happened to this one? Stapler missed this one. It has 4 problems. Yeah, these will just pass these back, and that has 4 problems on it. They're coming. One more? Here. This one's not stapled. All right, we can talk more about that later. I think you could probably handle the first one, maybe the second one. I did provide these online also in CDF format, so if you want to rotate things around and take a look at what you're working with there, and also in PDF format if you need to print it out. Now, little warning, I did post them earlier today. I realized there was a typo. I just updated it. So if you downloaded it earlier today, go back and get it because I just fixed it about an hour ago, right? All right, last time, do you remember what we were doing? Double integrals over rectangles, right? Now the homework for 12.1, I did the problems, selected problems, and I put that on YouTube. I also did the homework for 12.2 today, so that's on YouTube. You can watch that later if you're doing your homework. All right, so we're going to go now and get a little more general about our regions. We're not going to restrict ourselves to rectangles anymore. So that's what we did last class, right? We had a rectangle. We were integrating over this rectangle, so you know, the ground, that was the ground, right? The surface was above it. We were looking at the volume straight down. I told you there were going to be 2 types of regions we were going to look at today, type 1 and type 2. A type 1 region is any region D, we're going to use D instead of R. R is like rectangle. D is just going to be like domain, I guess. Our region D is the set of all ordered pairs, that's the points in 2-dimensional space, such that your x is between two constants, so that's just like the rectangle, right? But this time your y value is stuck between two functions of x, right? So it used to be with the rectangle that your y was stuck between two constants. Now your y can move around. So there's a picture of a type 1 region. Notice that this is very much like an area problem from Cal 2, isn't it? Like where you have your first limit of integration, your second limit of integration, then you were doing like this function minus this function. Remember that? I'm doing that in Cal 2 right now. That's why I'm saying, like, I know you do see that in Cal 2. That type 1 region is kind of a classic area problem from Cal 2. That's our region of integration. That's what we're integrating over. So when we draw our regions, it might be good for us to kind of draw like an arrow, like a line or something, that shows that the lowest value of y, right? This is the y direction. So the lowest value of y is determined by some function, right? G sub 1 of x. The highest value, right, is controlled by some other function of x. And then our x values just vary back and forth. So if I move x between a and b, it moves this line over. And again, it's the same function on top, same function on bottom the whole time. Yes? Any region that looks like that is called a type 1 region. And to integrate a type 1 region, we're going to do a double integral over the region D of the function f of xy with respect to what? Area, right? With respect to area. And this is the actual integral. So what's the big difference between this and what we did last time? There's functions as limits of integration, right? Instead of c and d, we have two functions. And because of that, you are not allowed to change the order of integration. You are stuck. If you're going to do a type 1 region, your constants, a and b, have to be the outside integral. And then the inside integral has to contain the functions. So your order of integration is fixed. If we have two surfaces, right? So now we have some surface f and then some surface below it g, and we want to know the volume between them. We said last time you just subtract the two, right? But that was over a rectangle. Here we can do the same exact problem, but over, can you all see that that's a type 1 region? Can you all tell that's a type 1 region? Okay, you've got your restriction on x, and then your y is in this direction, so there's your lower function, g sub 1 of x, g sub 2 of x. So it'll be the same thing that we did last class, the same formula, but again, did I have it there? Yeah. Okay, so it's just reiterating that you subtract the two double integrals, or put them together and subtract inside. Best way to do a problem, get a feel for this, is just to work one out. Find the volume under z equals x plus 2y. What is that if I graphed it? It's a plane. Find the volume under this plane on the region bounded by these two curves. All right, so let's talk about this region. I'm going to try and draw it first. Remember, this is my domain over here, right? This is what I'm going to integrate over. My guess is that this is going to be a type 1 region. Wouldn't you say? Okay, makes sense that it would be, right? All right, so let's graph y equals 2x squared. That's a parabola, right? Starts out at the origin. I'm going to do this. I'm going to use my colors today. So this is y equals 2x squared. And then 1 plus x squared is another parabola, right? Which opens up also, but it's moved up 1. It's also wider than this one is because 2x squared stretches you out or compresses horizontally or stretches vertically. So when I come here to 1, my parabola should go out like this and be wider. That is my region of integration. We okay with this? Yep. So that is y is x squared plus 1. Everybody comfortable with seeing the region that's bounded by both of those? So all of this stuff in here, that's D. So the question now to you is this a type 1 region? Well, it's not a rectangle, right? So we can't do what we did last class. So if you think it's a type 1 region, then you need to be able to draw a line or a little arrow in here like this vertically, and imagine moving this back and forth through your entire region D, and your top function should never change and your bottom function should never change. It should always be the same too. So is it, if I move that around, is the one that's red always on top? Yeah. Is the one that's blue always on bottom? Yes. So you see you have an upper and a lower function there? So the upper function is my g sub 2 of x. The lower function is what we call the g sub 1 of x. Does that make sense? Yes.
So, in the order of integration, which one would go on top?
2's on top, 1's on bottom. So the upper limit is going to coincide with the upper function. The lower limit of integration is the lower function. So it's good. It works that way, right? So I'm just going to write here, this one is x squared plus 1, and then this one is 2x squared. That all right? What's the other thing we need to resolve? Where they hit each other, right? Because where they hit each other is where I'm going to determine, or what's going to help me determine where I need to cut my x's off, right? X is going to have to be between here and here, right? That's the question. What's this A? What's this B? What are they? So you have to find the intersection points. So to find the intersection, you set the two functions equal to each other. Plus or minus 1. Subtract x squared to both sides, square root, plus or minus. So we know that this is A is 1, and, or sorry, A is negative 1, and B is positive 1. And at that point, you set up the integral. All ready? The double integral over the region D of the function of x and y with respect to its area will be equal to the double integral d, you tell me here. So dy, dx, dx, dy, which? dy, dx. Now the way you remember that is the outside integral has to have the constants, right? So the outside one is going to be negative 1 to 1, right? The next one, the inner one, is the restrictions on y. So the y restrictions were these two. So 2x squared on the bottom and x squared plus 1 on the top. And then the actual function that we're integrating is what? This right here, right? That's the surface above that we're trying to find the volume underneath. So x plus 2y. That's it right there. This is our type 1 region. Questions? Comments? Concerns? Integration time, right? So when I go to integrate this, I'm going to leave the outer integral alone. I like to put a set of brackets. Let's find the antiderivative of this with respect to y. So what do we have? xy plus what? Y squared. And we're evaluating that. Now this is where things get a little weird. Y is the variable, right? So we're going to let y be first the lower limit of integration, which was 2x squared. And then we're going to let the upper limit of integration be x squared plus 1. We're going to figure all that out, and then we're going to finish out the outer integral. So this is the first time we've ever done this, right? We've never before had to plug in a function into our antiderivative. So this will be equal to -1 to 1 integral, and then bracket. I will have two things when I'm done that I have to subtract. Figure out what that is, dx. So let's plug in to this expression for y, x squared plus 1. Okay? So x times x squared plus 1, I'll just put that here, x times x squared plus 1. And then plus y squared, so plus x squared plus 1 squared. Everyone see that? Then redo this again, but this time replace y with 2x squared. So x times 2x squared plus, what's y squared going to be? Square this. Four x to the fourth. I'm going to clean this all up first before I integrate it. Integral -1 to 1. I'll just do a parenthesis now. I'm going to have distribute through x cubed plus x. Can we square this? Plus 1. That's squaring that. Okay, this right here is 2x cubed, but I'm subtracting it. And this is 4x to the fourth, but I'm subtracting it. That. Do we have any like terms? We do have some, right? Questions? All right, let's put them in descending order. X to the fourth, we have -3. X to the fourth. Took care of those. X cubes, -1, so -x cubed. Got those. X squareds, only one of them, right? Then plus x plus 1. All right, so I've got everything taken care of there. That's trivial at this point. Is that trivial? Yes? ... So I'm not going to finish it. You know what to do now, right? All right. Okay, let's take a look visually at what we just did. You sure there aren't any questions? Comfortable with the antiderivative of that? I know my Cal 2 students would tell me, please give us like 100 of those on a test and we'd be happy, right? Just give us a bunch of those. So I'm assuming here you're happy to see that at that point. But you probably feel unsatisfied because I didn't give you like a nice numerical answer. There's the domain in two-dimensional space. There's that same domain laying on the ground in three-dimensional space. Here's the surface, which we said was a plane. Here's just the region there plugged in where it would hit the plane if you map those points up into the function. And that generates a solid if you look straight down. Let me pull all this junk out of here. It's kind of jaggedy. That's just because I have the computer not plotting a bunch of points. Damn it. There. We found the volume of that solid. Well, we didn't. We almost did. Okay? Whatever numerical answer you would have gotten for that represents the volume of that solid. All right, cool. Is this different? Yeah. But those aren't the same two curves. Okay. So let's just look at this one. So your function that you're going to integrate is x squared plus y squared, right? That's going to be your integrand. And now you want to look at the region bounded by these two curves. See, right now you know these are going to be type 1 because that's all we've talked about. But when you get to your homework in problems like 21 through 29, they don't tell you what type region it is. So you're going to have to determine that. And until I show you type 2, you still kind of don't know what I'm talking about. So just keep that in mind when I'm approaching this. I'm always looking at this as I don't know what type region that is until I draw it. So x squared, that's familiar. (2x). It's a linear function. Something like that. We all see the region? It's that little sliver, right? How do I know that 2x is above x squared? Yeah, I know, but I'm saying when I drew it, I put the red one up there. Like, why? How do I know the red one doesn't come out over here? Like, you could plot a couple of points just to verify. All right, that region is a little too small. I'm going to kind of make it bigger over here. I'm going to exaggerate it. My parabola is doing like this. And my line is doing something like this. And if I think that this region is going to be type 1, then I'm going to need to be able to draw a vertical double arrow like this and move it left and right and make sure that the red one is always the top and the blue one's always the bottom. And is that going to be the case? Yes? Okay, so what's the top function written as a function of x? G sub 2, right? And 2x. And then G sub 1 is the one on the bottom. And that's your x squared. What still remains to be found? The intersection, right? Now this one I think we can all agree we don't need to go find, right? 0? But we do need this one. So to find that, you set x squared equal to 2x, right? And what's your solutions? You get two of them, 0 and 2. 0 and 2. I'm not showing that, but that's what you would get. So this is 2. So as I slide this thing left and right, the x's are stuck between 0 and 2. The y's are stuck between two functions of x. It's type 1. We set up the integral, go to town. Yeah? All right, for this one, I'm just going to set the integral up. I don't think I'm actually going to do any of it. Unless you want me to. I'll take a vote. What's the bottom limit of integration here? It's g1, so x squared, and then 2x. And you can even put y equals if you want. Y equals x squared, y equals 2x, but I usually don't. The book doesn't either. What are we integrating? Yeah, that's our order. X squared plus y squared, and then dy dx. Okay? That's it. Integrate this with respect to y. Let's just talk about it. It would be x squared y, 1/3 y cubed. You'd go in, you'd replace y with those two things, figure that out algebraically, and then go back through, integrate that, plug in your x's, and be done. So dot, dot, dot.
Let's get on a test.
What's that?
Let's get on a test. Dot, dot, dot.
Dot, dot. Yeah, on the test, you just put dot, dot, dot. Yeah. All right, so then what is a type 2 region? A type 2 region helps you deal with regions that you have when the curves you're looking at are not functions of x. So this time, what we're going to have is we're going to have that our y value is trapped between two constants, and our x values are stuck between two functions of y. So it's basically a sideways picture of what we just did. You have your y's are stuck between two places. If you draw a horizontal double arrow, then your left x, right, your left x value is bounded by the red curve. Your right x value is bounded by the blue curve. And so the blue and the red functions are both functions of y. So we'll call this one h sub 1 of y and call this one h sub 2 of y. We just use h instead of g. And so what do you think the integral is going to be? Double integral. What do you think what's the order of integration going to have to be? It's going to be dx dy this time. You're going to have on the outside one the y's. So we use c and d so we don't confuse them with a and b. And then here it's going to be our, which one do you think happens first? H1, H1, and H2. So with G1 and G2, it was easy because you could say, G2 on top, G1 on the bottom. This one, it's H2 is the right one, H1 is the left one. Or if you turn your head side